Our next speaker is Thanakorn Khamvilai. He received his PhD from Georgia Institute of Technology in 2001, and he's currently an assistant research professor at the Department of Aerospace Engineering in Pennsylvania State University. His research interests include unmanned aerial vehicles, avionics, control, and optimization. Today, the title of his presentation will be Towards Intelligent Middleware for More Resilient Robots.
Hello, everyone. Thanks for attending my presentation. My name is Thanakorn Khamvilai. I will present my research on a topic of Toward Intelligent Middleware for More Resilient Robots. And since my background is aerospace, I will focus primarily on avionics applications. Let's start with the definition of avionics. The word avionics is the combination of the words aviation and electronics. Therefore, it simply means electronics components that are in the aircraft. These components form several systems. For example, a communication system, a navigation system, a display system, etc. However, there are some aspects that make avionics more special than electronics in other areas. The first one is the thing that aerospace engineers are trying to minimize, which are size, weight, power consumption, and cost. These things are obviously related to the cost and the performance of the aircraft. The other aspect is the one that must be maximized because they involve human life. This aspect is safety and reliability. There are a lot of documents and guidelines for ensuring safety in the system development and implementation processes. In order to optimize those important aspects, the architecture of avionics system has been developed over a century. The very first version of the autopilot was invented by Sperry in 1914. It is a mechanical gyroscope that helps stabilize the aircraft. Then we go to the electrical regime, starting with an analog and digital systems, which have a point-to-point communication. However, this point-to-point communication requires a lot of wiring. The new architecture called federated was invented to combine this communication into a single data bus, which reduced the weight of the aircraft. Next, in the Internet era, the Internet-based communication is adopted to the new avionics architectures called Integrated Modular Avionics. As the name implies, this architecture integrates components with the same functionalities into the same module to reduce the size of avionics systems. And now with the emergence of the new aircraft, like urban air mobility or delivery drone, there is a need to further reduce the size of avionics and to improve or at least to maintain the same safety and reliability as larger aircraft. It is possible to achieve this objective by introducing a new architecture called the second generation integrated modular avionics. This slide shows the comparison between the first and the second generation integrated modular avionics. In the first generation, each hardware contains both computing module and input-output ports, whereas in the second one, the input-output ports will be separated as another set of hardware. This provides a benefit of hardware redundancy management. Another difference is the introduction of platform-level services that truly separate between software and hardware. This does not only facilitate the development and modification process, but also provides a possibility to use dynamic software reconfiguration for reliability improvement. For these reasons, my research focuses on developing methods for redundancy management and dynamic software reconfiguration. In my research, those techniques are addressed. The first one is redundancy design automation. Given a component with a reliability requirement, we would like to find the minimum level of redundancy to achieve that requirement. This technique ensures that we can keep the size of the system at minimum while maintaining the desired safety or reliability. Second, I present the reconfiguration technique through the task scheduler part of the middleware. This one considers the initial assignment of software to hardware, as well as the online relocation of software that are affected by the hardware failure. The overall system reliability can be improved by using this technique. And lastly, these techniques are implemented in 3 different aerospace applications, which are Multicore avionics emulator, multi-rotor guidance and navigation system, and modular drones with actuator failure. Let's start with the first contribution. Consider 3 different types of components. denoted by a circle, a square, and a triangle. The first goal is to determine the minimum level of redundancy for these components to satisfy the reliability constraint. The method I used called a geometric programming, which is a subset of a convex optimization that has a benefit of providing a globally optimal solution. Once the redundancy is determined, we also have to figure out the connection among these components. Another convex optimization called sinomial program is used to solve this problem. Starting with a fully connected communication, we then solve this sinomial programming problem. The solution of the problem will provide only necessary connections that maintains the system reliability. This technique is applied to an Avionics full duplex switch Ethernet network, or AFDX. Starting with a single Ethernet switch, the entire network can be constructed to satisfy the required reliability. Now we look at the middleware. Middleware is a special type of software that glues together software applications, operating system, and hardware. In the embedded systems, middleware is usually referred to a real-time operating system, or RTOS. To illustrate the importance of middleware, let's take a control system, for example. This is a classical control structure. We can write a code for it. However, to execute it in an actual system, other software components are needed. To receive a feedback information, we need a sensor driver. Similarly, we will need an actuator driver for executing our control signal. These software applications must be executed in some specific order, meaning that the controller needs feedback data before it can compute the control signal. Therefore, we need a task scheduler to schedule these applications as well as the others that are used in our system. To schedule tasks, we also need timers. Tasks may exchange information, which means we will need inter-task communication mechanism. Memory management is also important, since we need to store the values of parameters for this software. We can see that several auxiliary software, which are defined as middleware, are required in order to execute our simple controller. This diagram shows the general stack of the system, starting from the high-level software application to the middleware and to the low-level hardware. There are some examples of high-level software applications that we may have heard, including computer vision, learning-based controllers, and path-padding algorithm. For middleware, there are also several components. However, the one I focus on is the scheduler. The reason being that having a good scheduler can provide several benefits to the system and eventually improve the system safety and reliability. Here is a partial list of popular middleware or RTOS used in embedded systems. Here is the list of popular scheduling algorithms. However, none of these algorithms can address all benefits that I have shown in the previous slides. Therefore, in my research, I propose an optimization-based scheduling method. As we all know, optimization has been used in many fields. In the control and robotics community, it can be used to plan a path for autonomous vehicles or other types of robots. In structural design, it is used to find an optimal shape for a certain type of load and stresses. In biology, optimization is used for solving a protein folding problem, which can enable quicker and more advanced drug discovery. In computer science, the optimization is used in deep learning and artificial intelligence to train various systems, such as object recognition from images. In the context of avionics, I use it to design a scheduling algorithm for middleware because it can address all benefits shown in the previous slide. This method will be illustrated by these three applications. Let's look at the detail of this optimization-based scheduling technique. It is modeled as a mixed integer linear program because the algorithm to solve this program is deterministic and can always provide the globally optimal solution. In addition, there are a lot of high-performance convex optimization solvers available, including both open source and commercial ones, which are fast enough to solve for a solution in an online fashion. Several objectives are included in the optimization problem formulation. The first one, which is obvious, is to maximize the number of running software applications. However, in the case of failures, where there is not enough resources to execute all software, the algorithm should prioritize the safety critical ones. To minimize the transient effect of relocating applications, only applications that are affected by the faulty hardware should be relocated. The execution of other software should remain the same. It should also provide a tolerance in case of the delay, latency, and any other uncertainties in the software execution time. And lastly, in case of a multi-core system, the maximum CPU utilization should be minimized. And like other optimization problems, this problem also has a lot of constraints to satisfy. In the first implementation, we look at the emulator of multi-core avionics. This shows the direct application of our problem formulation. The software relocation is performed in a decentralized fashion, which means there is no specific hardware dedicated to run the scheduling algorithm. The scheduler is considered as one of the software applications and can relocate itself. In addition, the software relocation is also performed in an online fashion in order to reduce the number of computation from n factorial to a summation from 1 to n, which can save a lot of internal memory for storing solutions. Besides, it can also handle partial failures, which can be unforeseeable at design time. The architecture used in this implementation is a mixture between an Ethernet-based communication used for transferring data between the electrical motor and the multi-core emulator, and a low-level communication network, which is in a square topology used for communication between each core. For the hardware, we used a Raspberry Pi to emulate the system. Here is the plot showing the result of the emulator. The y-axis on the left corresponds to the PWM signal, while the right one corresponds to the thrust. In this experiment, the controllers try to control the thrust to be around 100 grams. During the first couple seconds, when I pushed the motor against the sensor, the thrust went up and all of the controllers tried to lower the PWM. After that, when I released the motor, the thrust was controlled at 100 grams. When failures were injected and the controller applications was dropped, the PWM signal sent to the motor becomes 0. If at least two signals match, the motor remained in operation. If none of them match, the motor will be stopped. So as the case where the controller applications were dropped. The next implementation is software-in-the-loop simulation of multi-rotor guidance and navigation system. We consider a hexacopter with 6-core processor and 50 software applications shown in these figures. The simulation state machine is described by a sequence of action of the multi-rotor, starting with the multi-rotor being on the ground and taking off to the certain altitude. The mission is started, and the multi-rotor will follow the waypoints. During the mission, random failures will be injected to each of the processing core. Some of the software application will be dropped. However, if the safety critical ones are still running, the vehicle will continue the mission. If that is not the case, the vehicle will go into the altitude hold mode and eventually land itself if the failure keeps occurring. The list of software applications are taken from an open source autopilot named ArduPilot. The source code shows the properties of each application, which are the worst case execution time, period or deadline, and a priority. The software applications are then categorized into 5 levels of severity based on the guideline documents. Redundancy is applied to the safety critical ones, making the number of applications be 50 in total. Failure is injected to each processor during the flight operation by this failure injector in the bottom of the picture. The top plot shows the current execution of the task scheduler, and the remaining 6 plots in the lower half show the backup schedulers that will be executed in case of each processor failure. In this picture, processor 1, 4, and 6 are already faulty. Therefore, only 3 backup schedules are shown. The plot on the right shows the applications that are currently executed. There are three main blocks for the software-in-the-loop simulation architecture. The first one is the physical hardware simulator, which is LOS and Gazebo. This simulator takes in the PWM signal to generate forces and moments to the vehicles and returns the state of the vehicle. The second block is the safety critical tasks running on the simulated multi-core processor. These tasks are taken from ArduPilot, the task scheduler that is developed based on the proposed optimization method is also running on the multi-core processor. The third block contains external software that are used for fault injecting and monitoring and visualization. All the communication are done using the data distribution service library called OpenDDS. The video shows the operation of this hexacopter, starting on the ground and then take off to the certain altitude. During the operation, the failure will be injected to each of the processor. When the failure occurs, the applications that were running on that processor will be relocated to the other available processors. However, when there is not enough resource for the applications to be executed, the lower priority applications will be dropped.
Auto flight mode.
And if there is not enough to execute all of the safety critical applications, the vehicle will go into the fail-safe mode, which are the altitude hold and landing. As you can see from the current video, the vehicle is following the waypoint, and the first failure was injected to the first processor. The next failure was injected to the fourth one. We still have enough resource to execute the safety critical applications at this point. And the third failure is injected to the sixth processor. You will see that another two failures will be injected, and then there will be
altitude hold flight mode.
There will not be enough resources to execute all the software applications. In this case, the vehicle will go into the altitude hold mode, and then it will land itself later on.
Land flight mode.
The last implementation is on a modular drone that we use Pithawk with our custom firmware for the flight controller. For each module, there are 12 phases, so we name it a dodecacopter. The assembly of modules can be made into various configurations, such as a hexacopter shown in the top left, a quadcopter shown in the bottom right, a tetrahedral configuration shown in the bottom left, and a configuration with 10 modules shown in the top right. Each configuration has its own benefits, such as controllability, power consumption, and redundancy. The hexacopter configuration is used in this experiment due to its fault-tolerant capability. Since the drone is designed to hold avionics system and the motor within the same frame, it implies that the failures on the processor will also lead to a stop in the motor operation. Each module of the dodecacopter contains several hardware components, such as the flight controller, remote control receiver, Wi-Fi module, battery, motor, and ESC. Each module talks to one another using both wired and wireless network. The experiment was performed indoor, where the position and velocity of the vehicle are captured by the beacon camera system. Each module sends its information to the ground station via the Wi-Fi router and also receives signal from the safety pilot. This video shows the experiment of our vehicle with a failure injection to one of the modules. It currently shows the normal operation where all of the 6 modules are working properly. The failure will be injected to the vehicle by unplugging the battery. And we will show that the failure on the processor also implies the stop in the motor operation. In this slide, we will show that with the software reconfiguration, but without the control allocation, the vehicle will not be able to hold its own position. And this we will show the flight with both software reconfiguration and control allocation. You see that the vehicle can better hold its own position. We will also show the in-flight software reconfiguration. In this video, you will see that the motor on the bottom left will be ejected by a failure, and the vehicle still remains in operation. This plot showed that using control allocation with the software reconfiguration is necessary for the vehicle to hold its position. In addition, the distribution of control signals is smoother comparing to the case without the control allocation. In summary, my research proposed an optimization-based framework for the redundancy design of network system and the software reallocation of networks of hardware. In addition, there is an implementation of the proposed framework on various applications. For the future research directions, I will focus on development and implementation of optimization or other intelligent techniques on other aspects of middleware, RTOS, and avionics systems. Also, I am interested in an integration and certification of multi-core processor in modern aircraft like urban air mobility and fixed-wing vehicles. Lastly, I would like to thank all of my research sponsors from both government entities and private companies, as well as all of my friends and colleagues from Georgia Tech and Penn State University. And more importantly, it is my honor to have a chance to present my work here at KAUST. I will then open a floor for Q&A session.
Thank you a lot, Professor Khamvilai, for the amazing combination of hardware and software. Fantastic presentation, by the way.
Thank you.
If you are ready now for the question and answer session, I would like to invite the audience to ask for questions.
Thank you for the nice talk. So I didn't get when you talk about the processor fault. What do you mean by processor fault? Is it an actuator fault or sensor fault? I saw in one of your application example, the fault was injected in the battery. So I did not really know what does it mean. And the second thing is when you have, for example, kind of malicious attack which is different to the fault. How can you handle this situation?
Yes. So for the fault, in this case, I consider the failure of the processing unit. However, in our vehicle, the actuator is directly connected to that processing unit, which means when there is a failure on the processor, there also implies the failure on the actuator as well. And for the second question, when there is a fault, there will be a signal sending to the other processor that there's a failure on this module. So basically, when there's no failure, the module will talk to each other and they will know which one is still alive. And when there's a failure, that signal will be stopped. So the other modules will know that the faulty one is dead, basically. Does that answer your question?
Yes, thank you. I would like to thank you one more time, Professor Khamvilai.
Thank you so much.